Sorry. Bit pala ako. Right, good afternoon, everyone. For today, we will be talking about groundwater recharge. And okay, and this is just part of how we study groundwater. Okay, if you remember the water budget equation, okay, it's always difficult to directly measure how much groundwater are you recharging or how much groundwater is available. But it's relatively easier to know how much runoff, how much evapotranspiration, and and other surface processes are you losing, how and how much water are you losing or gaining to other surface processes. And yeah, and we are here to discuss, of course, first the recharge, which is basically derived from precipitation. Okay, and of course, when you have the precipitation, and if you want to know the groundwater recharge, all you have to do is to eliminate how much precipitation water is lost to runoff and how much is lost to evapotranspiration. And from there, you can basically just estimate how much groundwater recharge are you getting. Right? And for runoff, it is important to understand basically what is your soil type. Is it clay? Is it sand? As well as the antecedent or the existing moisture. This is more on related to the long-term climate, weather or climate conditions, especially when you're dealing with dry and wet seasons. Okay? And also land cover. You will see later how land cover affects runoff. Right? Now, in general, soils that are well drained are soils that are well drained, okay? Meaning soils that easily drain out water, such as sand, generally have high porosities and high hydraulic conductivities, meaning they can potentially store a lot of water because of their high porosity, and they can also transmit water relatively quickly because of their hydraulic conductivity. Land cover usually determines the fraction of precipitation available for infiltration. And you can appreciate that, for example, for urban areas where, for example, Metro Manila, where most of your land is already covered in concrete or pavement, you have, in the case of that, you have very limited land area that's actually available for infiltration, right? In contrast, when you're dealing with vegetated open fields, okay, like in the provinces, you have more open area that is actually conducive to infiltration of water, right? And available rainfall will infiltrate the subsurface until the rate of precipitation exceeds the infiltration capacity of the soil. That simply means that you will get infiltration, but it's not infinite. Infiltration will only occur until you saturate the soil. Once you have saturated the soil, you will basically start getting ponding, and the ponded water can eventually start moving as runoff, and it can actually enter your streams or rivers, or worse, if they accumulate a lot, they can end up as floods. Okay. Sorry, akala ko na discuss ko na tong lecture. Chinek ko lang. So, hindi ko pa pala siya hindi-discuss. So, okay, tuloy lang natin. Ah, okay. And I think I already discussed this in exercise 1, or maybe not. Anyway, this is just how infiltration occurs. Okay. I think na-discuss ko na to. Okay. Basically, yeah, you just you're just in here, you're just getting infiltration. This is infiltration. This is infiltration until you reach the point where the soil gets saturated. Okay, by saturated, it means all the pore spaces in the soil are filled with water. Once you hit that point, you will get ponding, and basically you will get very, very limited infiltration. Okay. At that point, you will be getting more runoff production than actual infiltration. Okay. That's why when you have storms, it's possible that you may not actually, storms and heavy rainfalls may actually not really effectively cause recharge of the groundwater. Okay. Because of their, in those cases, you might be getting more ponding and runoff production. Okay. As opposed to rainy season, where you have probably daily rainfall, but the rainfall may not be as intense. Okay. Such that you're just continuously getting steady amount of infiltration over a long period of time. Right? Now we can actually calculate how much runoff can we expect. Okay? And this is where this model comes in, the Soil Conservation Service, or SCS, runoff curve number method. Okay? This is a method that's commonly used in hydrologic models to actually calculate the runoff, okay, in watershed basins, as well as calculate the water retention volumes. Okay. And what this model or method does is that it takes in the input precipitation, the input infiltration characteristics of the soil moisture, antecedent rainfall, meaning the previous rainfalls, land cover type, impervious surfaces, and surface retention. Basically, it's just right. Let's resume the lecture. Okay, and once you have all these input parameters, okay, you can basically just um calculate what's gonna happen to your watershed. Okay, you can even do flood modeling. Okay, okay, and yeah, from there eventually you can just calculate the peak discharge, or basically the highest amount of water flow that can occur on a given river or river section. Okay, and yeah, you can use that for other stuff like flood modeling or designing bridges and stuff. Right. You have here an equation to calculate runoff, or Q. Runoff is just the volume of water that's flowing through time. Okay. And this is just related to your rainfall. The more rainfall you have, the more runoff you get. And it's inversely proportional to your initial abstraction. Therefore, the more abstraction you have, the less runoff you get. And it's also inversely proportional to your potential maximum retention. Okay. So the more retention you have, the less runoff you get. Now, what are these parameters? Abstraction is basically all the processes that contribute to loss of water, such as evapotranspiration. On the other hand, retention is more of the storage of water in the surface, particularly ponds, okay, and so on. Okay, but let's discuss that later on. Okay, initial abstraction is all the losses before the runoff begins. And that can include, of course, water in the surface depressions like ponds or yeah, topographic lows. Also, the water lost to vegetation, evaporation, and infiltration. Okay, and this parameter abstraction can actually be correlated with your maximum retention. Okay, and once you plug in this relationship into the previous equation, we can simplify it so that the runoff is just relate can be computed relative to the precipitation and your maximum retention. Now, retention or S, which generally includes infiltration and loss due to vegetation and evapotranspiration and storage, you can estimate that number using the curve number parameter. Okay. And this number ranges from 0 to 100, where 100 is a perfectly impervious surface like a concrete road or a concrete surface or a probably fully saturated clay soil. And notice that the higher the curve number, the lower the surface retention. Okay? Which makes sense because when you have a higher curve number, you usually have a more impervious land surface. And when you have a impervious land surface, you're basically limiting all the water that can be retained in the soil by means of infiltration and other processes. All right. And okay, you can see here how you can estimate your curve number values. Okay. The rows here correspond to your land cover type, and the columns here correspond to, you have here your hydrologic condition. You also have your soil types, A, B, C, D. Okay. Right. Sorry for the interruption. And you can see here, for example, if you have a wood or grassland area, you can just check or basically just look at the hydrologic condition here. So you have poor, fair, and good. In the footnote here, okay, generally poor is when you have less than 50% ground cover, and fair is when you have 50 to 75% ground cover or meaning vegetation, and good is when you have more than 75% vegetation. For example, let's say you have a good a wood grass area that has like 80% ground cover, you can assign it to the good hydrologic condition. And then the next step is to just look at the soil type. You have A, B, C, D. A corresponding to sandy loam, loamy sand, and sand. Okay. And then B is silt loam, and then C is sandy clay loam, and then D is variants of clay and silt. Okay. So let's say, for example, you have a sandy clay loam soil. You can basically just choose this number for this land cover and soil type. Okay. In the Philippines, you can actually obtain soil maps from the Bureau of Soils and Water Management. I think it's under the Department of Agriculture. Okay. And then usually for the land cover, you can just base it on the satellite images like Landsat or even Google Earth. Okay. All right. Now let's talk about the curve number and the calculated direct runoff. Okay. What this chart is just trying to show you is that the more the higher the curve number, the more runoff you can get. Okay. At least you can see here when you have a curve number of 40, okay, and you have like 10 inches rainfall, you'll get a corresponding runoff of around 2 inches. As opposed to a soil with a curve number of 100, you're getting something close to like 10 inches or almost 100% conversion of rainfall into runoff, right? That's one of the reasons why, or at least one of the quantitative um not evidences, but it sort of supports the observation that you tend to get more floods when your watershed becomes more and more urbanized. Okay. Or of course when you're also removing vegetation from your watershed. Mainly because as you remove the vegetation or as you start paving or concreting your land surface, you become more and more efficient in converting rainfall into runoff. All right, now let's move on to the other part of the hydrologic budget, which is your evapotranspiration. Okay, you can see here you have a cartoon showing basically how your moisture goes to the root system of your plants and trees up to the vascular system until it exits the vegetation through the pores of your leaves. Okay. It is easily the second largest component of water budget next to precipitation. That also means that evapotranspiration, okay, as you know, precipitation is your only source of water. Okay? It's the only way water can get into your watershed. The rest of the components in your hydrologic budget is mostly about consuming water. Okay? Probably except for groundwater storage. No? when you're getting negative groundwater storage, you're actually putting water into the surface. But anyway, evaporation, this component is very, very huge when it comes to consuming water. Okay, so it's actually the largest component when you're talking about how water is consumed in a watershed. Okay, and of course, if you're concerned about conserving groundwater recharge, okay, you may look at ways to actually limit evapotranspiration. Right? And I think we already discussed this in the first exercise. Okay? Reference crop evapotranspiration is basically a calibrated value, okay, or basically a reference value for evapotranspiration when you have an ideal height of grass crop, ideal height of albedo or sunlight reflect or the reflectivity of your land surface, and I think surface resistance. I think this is related to the wind. Okay. But I'm not going to discuss that in detail because this is more of a meteorological topic. Okay. You can also refer to the Penman-Monteith evapotranspiration method. Okay. But again, I'm gonna skip this topic. Okay. And the point here that I'm trying to show is you basically when you're trying to get evapotranspiration, you can start with your pan evaporation data. This data is basically the amount of water that is lost to your evaporation pan. Okay, I think Pag-asa and agricultural colleges usually record this data. Okay, so you can probably request these kinds of data from Pag-asa or from universities or college that have agricultural studies. Now, when you have evaporation data, you actually have to convert it into evapotranspiration data, or you can use it actually to estimate evapotranspiration by multiplying it by your pan coefficient. Okay. And from there, you can get the reference evapotranspiration, which you still have to convert into a value that's actually more suited to your actual site conditions. All right. So it's quite a complicated process. Right. And this is just an evaporation pan. Okay. As you can see, you have a basin that is filled with water. All right. And basically, actually, this is not just an evaporation pan. I think this is a complete weather station because you also have a wind, I think a wind meter, wind vane. This component is most likely a rain gauge. Okay. And usually, modern instruments will typically have means to actually record the data digitally. Okay. And store it and also transmit it to your office or to your server. Okay. More or less, it's already the standard. Okay. At this time. Okay. Now let's talk about the Vados zone. So we have finished talking about evapotranspiration. Now we can talk about the Vados zone, which actually plays an important role in the recharge of groundwater. Vados zone is basically the transition zone from the surface to the aquifers or to the groundwater. Yeah, basically it's the transition zone between the surface and your aquifers, or between the surface and between your groundwater. Okay. By the term VDOS, it means that it's a soil that is not always saturated. It's the unsaturated zone. Whereas your groundwater is your saturated zone. Okay. Groundwater and aquifer, that's your saturated zone. And VDOS zone is the sorry. Sorry for that. VDOS zone is where your infiltration process is happening. Okay. And it involves a slow movement of water compared to the movement of water in the water table or in the aquifers. Okay. Okay, and infiltration is basically a function of your soil properties. For example, clay, for of course, will have a very low permeability or infiltration rate as compared to sand or fractured rocks, which can have very, very high infiltration rates. Also, you have to appreciate how infiltration works when you have a layered soil. So, for example, you have here sand. Let's say your first layer is sand, and then your second layer is clay, and then your third layer again is sand, right? Normally, when your water is percolating, okay, like from the surface, you can expect a generally fast infiltration rate in this sand layer. But once it encounters an impervious layer like a clay, you can get a very, very slow infiltration rate. Okay. And once it goes through that clay layer, you'll basically still get a slow infiltration rate because you're getting a very limited amount of water passing through this layer. Okay. Therefore, in this case, this clay layer is basically controlling the overall infiltration rate for this soil. Okay. There are other factors that can actually modify the infiltration rate in soils. For example, when you have soil that is unsaturated, meaning the pores are not totally filled with water, you can get very low or slow infiltration rate. Okay? But once you actually saturate the soil, you can get a very, very high infiltration rate. Okay? Okay, let's talk about the matrix potential. Okay? Basically, this is one of the reasons why we have a very slow infiltration rate in your VDOS zone. Okay? Now, what is matrix potential? This is also known as your soil water suction or capillary potential or capillary pressure head or suction head or matrix pressure head, tension, and even pressure potential. As you can see, it is called in many, many different but same terms. Okay. Anyway, it's an important parameter or important phenomenon occurring on your in your unsaturated soils, wherein you're getting an upward suction. Okay, meaning the soil is actually sucking the water upwards due to capillary and adhesive forces caused by the air in the pore spaces. Okay? It can only occur in unsaturated soils. Okay, so note that it can only occur when your soil is not fully saturated. Okay, and it involves a negative pressure. Okay, basically it literally sucks. Okay, because you have a negative pressure. And when you have a negative pressure, basically what's happening here is that your soil is basically pulling up your water. Okay, and it could result in actual slowing down of movement of water, or even complete uh, halting of the water movement, or even it can actually cause the water to move upwards instead of downwards, hence decreasing your infiltration. Okay. And generally, matrix potential becomes less negative until or weakens with increasing water content. It will eventually reach zero once you fully saturate your soil. Okay. The takeaway here is when you have a very, very dry soil, you can have a very limited infiltration because of your matrix potential. Okay. Basically, when you have a dry soil, the water is basically just getting stuck inside the soil until eventually you once you end up saturating the soil. Okay, you will eventually get zero suction head, and the infiltration of water will eventually be at a maximum rate. Okay, so that's the reason why it's actually bad when your soil is actually very dry, and then you suddenly have a storm or a suddenly heavy rainfall. In that case, you may get very, very little infiltration, and you may actually end up getting a lot more runoff, okay, than with a soil that's actually partial, that's actually quite moist. Okay. All right. And you can see here the relationship between the saturation of your soil versus your suction head. Okay. This square line is your coarse sand. Right. As you can see here, saturation 1 is your 100% saturation, while 0 is when you have a completely dry soil. And when you have a completely dry sand, for example, you're getting something like a negative 200 centimeters of suction head. Okay. And as you increase your saturation, this will eventually drop down and flatten a bit until you reach zero suction once the sand is fully saturated. You also have another plot here, which is your circles. This is your fine sand. Generally, you have a very, very high suction head for fine sand. I think that's around something like 400, negative 400 centimeters of suction head. Sorry. Negative 400 centimeters of suction head. Once you increase your saturation, this suction head will eventually drop and will eventually reach zero once you reach 100% saturation. You can notice here that for the finer sand, you have generally more suction head compared to your coarse sand. Why? This is because matrix potential is a function of surface area. The more surface area you have, air, uh, the more pore spaces with a mixture of air and water can form suction. Okay. Now let's talk about actually groundwater recharge. And this recharge has a variety of factors. For climate, generally, when you have a cool and wet climate, you have minimal evapotranspiration because you have a cool climate and generally wet weather. And you also get a lot of precipitation. This is the most ideal setup for maximum groundwater recharge. Okay? The opposite probably is a hot and dry climate, such as in deserts, okay, where you have a lot of evapotranspiration and you have very minimal precipitation. Also, other local factors like mountain microclimates generally can receive more precipitation than lowlands. One good example of a mountain microclimate is here in the Philippines is the Cordillera region versus the Ilocos region. Basically, if you will draw a topographic profile from Ilocos up to the Cordillera range, okay? Okay, this is basically what it looks like, no? Okay? Basically, you have a mountain range in the Cordilleras and you have a lowland in the Ilocos area. Now, when you have your basically rain clouds or basically the general moist air is moving, it will essentially just collide with the Cordillera range, and this will result in precipitation on the side of Cordillera. Okay, that's one of the reasons why you generally have a very cold and humid microclimate in the Cordillera. It's basically just swallowing all the moist air. Okay, it's basically intercepting all the moist air coming from the east. Okay, and once this moist air passes through Cordillera, it's already deprived or basically it's already a relatively dry air. No. Now, once it reaches the Ilocos region, of course, all the moisture has already been consumed in the Cordillera area. And what you will get in Ilocos is basically generally dry air. So you get minimal precipitation and you get formation of sand, basically desert areas like the Pawai sand dunes, okay, and so on. Okay. Now going back, mountain microclimates, of course, generally receive more precipitation than lowlands because of the process that I described earlier. It's called the orographic precipitation. Okay. All right. And you also have this diagram showing Sorry. This diagram showing how the groundwater can flow from a mountain area to to the lowlands. Okay, you have some regional flow paths in here that's actually coming in from very distant areas within the mountain block, and you also have highly localized flow paths that are coming in from the smaller portions or localized portions of the mountains. Okay, that's why in mountain areas, especially in the Cordillera, you can easily get springs or even high water tables, even if it seems that the area seems to be relatively flat, or like when you have an area that's actually quite far from another mountain. Okay, so you can have these regional flow paths that can come from a long distance and actually contribute to the groundwater recharge or groundwater flow on another distant area. Now, in terms of geology and topography, generally when you have thin layers of permeable soils like sand and gravel, your area is relatively conducive for groundwater recharge. Also, when you have vertically bedded rocks, like in this photo, you have vertically bedded limestone or fractured rocks with vertically oriented fractures or joints. You can have very, very high recharge. Okay? In South America and I think in Northern Africa, they have very, very large aquifers that are actually based on sandstone formations, okay, which have highly fractured areas for recharge. In karst areas or in limestone areas, the mature portions can have the highest recharge. Okay? Basically, because in mature areas of the karst, you have very, very huge sinks or large caverns that can actually take up a lot of water from the surface. In terms of topography, gentle and flat slopes are more conducive for ponding and infiltration and recharge. Okay. And mountains, of course, can create precipitation shadows on the leeward side. So this is what's happening in your Ilocos region. Basically, your mountain here is your Cordillera region, and you're basically getting precipitation shadow on the Ilocos side of your side of the Philippines. Other factors, of course, urbanization affects your increases your the or rather modifies the imperviousness of your soil. Also, agricultural activities, okay, can actually increase recharge, but the recharge is actually artificial because it's mostly due to irrigation. Okay. And most of the time, the irrigation, especially in the Philippines, some of our irrigation are actually coming from the groundwater. So any increase in recharge due to irrigation might actually be canceled out because it's basically extracted from the groundwater. All right. Okay, I think I can still continue with the lecture. We're just like 10 slides away. Now let's talk about estimating groundwater recharge, or basically how hard it is to estimate groundwater recharge. First, we can talk about the lysimeters, which are basically containers that are placed below the land surface, and they are meant to collect percolating water to measure the infiltration. Although note that infiltration is not equal to recharge. Okay? It's always possible to get infiltration into the shallow groundwater, which will eventually go to the streams. Okay, so in effect, you can get a lot of infiltration while having minimal recharge, no? Because infiltration can actually infiltrated water will not always go to the groundwater. Sometimes it can jump to another stream or river. Okay. Lysimeters are usually used for calibration of numerical models, or basically for large scale studies. And usually it can only monitor deep it cannot monitor deep aquifers, no, so it can only measure the upper 3 meters of your subsurface. Okay. Also, it cannot detect or measure infiltration recharge from remote sources. So if you're working on a mountain area where you can actually get recharge from a very distant mountain, lysimeters will be of very limited value, right? Now let's talk about the other methods. This is one is a lot more practical, the water table fluctuation method. And here you're basically observing the rise in water table after a rainfall event. Okay. The principle here is that if this is your water table before a rainfall event, so let's add a rainfall event here. Okay, so let's say we have a rainfall event. So let's say you have this water table and you have this rainfall event, and after that, you get an increase in the elevation of the water table. The principle here is that you can actually just measure how much or by how many meters. For example, you can just measure the rise in the water table and just correlate it with the aquifer properties in that watershed. And from there, you can estimate how much water was, or what is the volume of water that was actually that has actually entered the groundwater. Okay. So again, you have a water table, you have a rainfall event, and after that you get a rise in the water table. What you can do is just measure that rise in water table, and from there, you can just multiply this number by the area of your aquifer and other correction factors related to the aquifer properties. And from there, you can easily calculate the volume of groundwater recharge. And from there also, you can correlate it with the amount of precipitation that happened during that recharge. Okay. So that basically that's how water table fluctuation method works. Okay. You can also do a double water table fluctuation method, but this one is a lot more complicated. So I'm just gonna skip this one for now. You can also look at the environmental tracers, but this is mainly for measuring how many days or years it takes for the water from the surface to reach your groundwater. Okay. The idea here is to as much as possible extract water or only extract water from relatively young groundwater uh, or young aquifers. No? Basically, the aquifers that are like a few years or a few months. Okay. Or when or aquifers that only take a few days to a few years to get recharged. Okay. Because it's totally possible to extract water from aquifers that are like 2,000, 3,000 years old. Okay. Meaning these aquifers are taking like thousands of years to get water from the surface. Okay. So at that point, if you're extracting water from very, very old aquifers, you're literally just mining or you're basically just drawing out water from those aquifers with no prospect of any actual time for recharge. Okay. Meaning you're basically extracting water from them faster than they can actually recharge. Okay. Another method is the base flow separation method. And this comes from the premise that stream flow is actually a mixture of different components. Basically, when you have a stream or a river, it essentially will consist of one, your direct precipitation. So basically, all the raindrops that are falling on that river. You also have your runoff collected from the stream, or basically the water uh, that's coming from the surface. And you also have what you call near surface flow from newly infiltrated water. This is basically the water that has infiltrated the shallow soils. And these shallow soils can actually end up um, discharging their water into the stream. Okay. And finally, some components of the stream flow are actually coming from your groundwater inflow. Okay. So essentially, we're just lumping together 1, 2, 3 as surface runoff. So these are all surface runoff and the rest is groundwater inflow. Okay. And then we also have to assume that the groundwater inflow into the streams come only from the groundwater recharge. Okay, so this is an important assumption. We assume that all the groundwater stream inflow is coming from the recharge from the aquifers. And this method is only applicable when you have a storm event. Okay. The idea here why we want a storm event is that when you have a storm event, you get a heightened amount of groundwater recharge. And supposedly when you have a lot of groundwater recharge, there's also a tendency for the groundwater to actually um discharge a lot of water into the stream. Okay. So this method should not be used in the following situations. First, you cannot use it on a karst terrain because karst terrains have a very complicated recharge, very complicated watershed. Okay, usually the topographic watershed of karst areas do not correspond to their actual recharge zones. Also, you cannot use it on a non-permanent stream. So you have to use it on a permanent river or a permanent stream. And you cannot also use it on in areas with abundant riparian vegetation or in areas with very extensive floodplains where you can get where you're actually losing a lot of water to evapotranspiration. And you cannot use it in areas with deep aquifers. So this is not useful for mountain areas because in mountain areas, of course, you can get a lot of water from distant or deep aquifers. Also, you cannot use it in an area that is actually being affected by a dam. Right? And the step is as follows. First, you draw a hydrograph or basically a stream discharge versus time. And this should involve a storm event. Okay. And you can use a variety of methods. Okay. And your end goal is to delineate the contribution of base flow and surface flow in the stream flow diagram. This line is your hydrograph. This is just a plot of your time versus your discharge. Okay? And what we're doing here is the ABC method where we are basically starting with the A. A is the inflection point, indicating the onset of surface runoff due to a storm. So this is your inflection point where your discharge has dramatically increased. And then point B is the point of your peak discharge, this one. So this is A and this is B. And then this point C is basically the point where the discharge has started to flatten. Okay? So basically what we're doing here is we can just from point C we can just draw a straight line that's parallel to the flat to this generally straight line. We just draw it straight, and then from the point B we just project it vertically downwards until they intersect at this point. Okay? Once we've done that, we can just basically connect point A, point B, and point C. Okay? And this part is essentially or basically this all the area underneath this line is your base flow or the flow due to groundwater recharge. Okay? That's the basic principle of your um what do you call this? The base flow precipitation method. Okay, there are other methods like the ABD method, but I think not gonna discuss this at this point. All right. That concludes our lecture for today. Okay. At this point, do you have questions or clarifications? So I think there are no any further questions at this point. I will just upload a copy of this lecture. Okay. And regarding the exam, we will still have a module exam next week, but it will be just a multiple choice exam or probably fill in the blanks and multiple choice. But of course, I tend to emphasize more on the exercises. So expect the exam to be relatively easy, no? So just make sure, no, that you finish the exercise, no, by next week. Okay, so thank you for attending this class. Okay, so i-end ko na lang yung meeting, no? Okay, thank you for attending.